For as long as humanity has looked up, our concept of survival has been tied to the light. But deep in the interstellar void, drifting silently far beyond the reach of any star, lies a completely dark world that researchers are now evaluating as a location for human survival. For centuries, the scientific consensus held that a host star was a non-negotiable prerequisite for life. A sun defines the habitable zone, providing the energetic foundation to maintain liquid water and sustain biological ecosystems. Our sun blasts the top of Earth's atmosphere with over 1,360 watts of energy per square meter. Without that continuous stellar influx, a typical rocky planet radiates its heat away, and surface temperatures instantly drop toward the cosmic microwave background, roughly -270 degrees Celsius. Yet planetary formation is a violent, chaotic process. Computer simulations of orbital dynamics show that developing solar systems are prone to gravitational scattering. Frequently, young rocky worlds are aggressively ejected from their native orbits and cast out into the galaxy. These are rogue planets, untethered cosmic vagabonds drifting in perpetual darkness. But rather than being dead, frozen rocks, modern geophysics suggests these orphans might harbor hidden oases of warmth and the ingredients necessary to support life. Decoupling habitability from stellar radiation means the total volume of potentially habitable real estate in the Milky Way increases by orders of magnitude. To understand how a sunless world stays warm, we have to look past the freezing outer crust and examine the geologically active interior. Isolated from solar radiation, a rogue planet relies entirely on internal energy. Deep within its rocky mantle, radioactive isotopes constantly decay, converting radiation into thermal energy, a process called radiogenic heating. This chart shows the scale of that energy output. On an Earth-sized planet, radiogenic heating provides a tiny surface heat flux of about 0.08 watts per square meter. Compared to the 1,360 watts provided by our sun, the energy deficit is massive. Because this internal heat is so weak, the planet cannot afford to lose any of it to the vacuum of space. To avoid freezing solid, a rogue planet must possess an exceptionally thick, perfectly insulating layer to trap that radiogenic energy. Surviving in the dark is a problem of thermodynamics. The internal geophysical engine replaces the star, provided the planet has an effective thermal blanket. One thermal model requires the planet to be ejected very early in its formation, escaping the destructive solar winds of its host star. This allows the rogue planet to hold on to a massive primordial envelope of hydrogen gas. This research paper details how that atmosphere functions. Under massive pressure, hydrogen molecules collide frequently, creating transient dipoles that block thermal infrared radiation. This extreme greenhouse effect effectively bottles up the planet's internal heat, raising surface temperatures enough to sustain liquid oceans. But an ocean under this atmosphere is a brutally hostile environment. The sky is pitch black. The pressure rivals Earth's oceanic trenches. Colonies must synthesize their own oxygen and use atmospheric hydrogen for fusion. While a surface ocean exists under a hydrogen greenhouse, the physical pressure renders large-scale human colonization a massive engineering challenge. If the rogue planet loses its gas atmosphere before being ejected, the surface water immediately freezes solid. This triggers the Steppenwolf planet model. Looking at this geophysical breakdown, we see how water ice acts as an excellent thermal insulator. If the outer ice crust is between 10 and 15 kilometers thick, it traps the rising radiogenic heat at the boundary where ice meets the rocky mantle. At that exact depth, temperatures reach the melting point, resulting in a global subsurface ocean heated from the bottom by glowing hydrothermal vents. To survive here, humans would drill through miles of hyper-hard cryogenic ice. We would establish submarine habitats on the ocean floor, extracting geothermal energy and relying on deep-sea chemosynthesis for life support. By utilizing miles of solid ice to shield against cosmic radiation, the Steppenwolf model creates a self-sustaining biosphere protected by the planet's own crust. Proving the existence of these worlds presents a severe observational challenge. Because they emit absolutely no visible light and orbit no host star whatsoever, they are virtually invisible to traditional telescopes. The elegant solution relies on Albert Einstein's fundamental theory of general relativity. When a massive rogue planet passes precisely between Earth and a distant background star, its gravity bends and magnifies the star's light. This temporary brightening is known as gravitational microlensing. This table shows the success of the technique. By analyzing the light curves, astronomers have detected free-floating objects with masses comparable to Saturn, Mars, and Earth. The 2024 data explicitly confirmed direct mass measurements of these untethered worlds. Statistical analyses derived from these detections suggest that terrestrial rogue planets likely outnumber stars. This implies a population of hundreds of billions, or even trillions, of free-floating rocky worlds occupying the dark spaces of the Milky Way. To map this previously unseen population, NASA is carefully preparing the Nancy Grace Roman Space Telescope for a 2027 launch. Equipped with highly sensitive infrared sensors, Roman will conduct large-scale surveys designed to catalog hundreds of these low-mass hidden planets. Billions of years from now, as the sun dies, human civilization could survive deep beneath the ice of a rogue planet wandering the galactic night.